but I'm. All right, good morning, everyone. Hope you had a nice trip in the snow. So let's see, tonight is homework number 1's due date. I looked on Prairie Learn, most of you have already done it a long time ago, so that's great. If you haven't, get it done by midnight tonight. And then homework 2 is on Friday at midnight. And then just a reminder that our labs and tutorials will start next week. So for the labs, I'll talk more about the labs on Friday, but there will usually be pre-labs that you will complete before the start of your lab. But next week, we're going to start with lab 0, and there is no pre-lab for lab 0. Okay, good. So what we were talking about last time was Coulomb's law, which was the force between 2 point charges, say Q1 and Q2, separated by a distance r. And we found that the force was equal to some constant, Coulomb's constant, times the product of the charges, and then divided by the square of the distance between them. If those charges were like charges, both positive or both negative, it was a repulsive force. And then if there were opposite charges, it would be an attractive force. Okay, this constant Ke is called Coulomb's constant. It has a value of 9 times 10 to the 9 and units newtons meters squared per coulomb squared. And it could also be written in terms of this permittivity of free space, this Greek letter epsilon with the sub-zero. So 1/4 pi epsilon naught is another way of expressing Coulomb's constant, where epsilon naught is this 8.85 times 12. Okay, we started working on an example. In fact, we finished most of it. I just want to do the last couple of steps here. The example was we're going to suspend 2 identical masses from some strings, and then we're going to give identical charges on those masses. So because of those identical charges, the masses will repel one another from an electrostatic interaction. And the question was, what angle do the strings attached to the mass make with vertical? So all we did to solve this problem is we drew a picture and identified all of the forces acting on each of the masses. We drew a free body diagram for one of them. It would look the same for the other one. There's a gravitational force down, there's the tension along the direction of the string, and then there's that repulsive electrostatic force. We broke those up into components along the horizontal x-axis and the vertical y-axis. Along the y direction, we could do an analysis. The net force in the y direction would be 0. That led us to an expression for the tension. And then when we do the x analysis, that led to a second expression. And we ultimately ended up with this funny thing where cos theta over sine cube theta was equal to all this stuff on the right, 4mg L squared divided by Coulomb's constant and the square of the charge. Okay, but the original question was to actually find an expression for theta, and we haven't really done that because our theta is stuck inside these complicated trig functions. Okay, so what we're going to do is to find an expression for theta. We will assume that theta is small and make some approximations. Right, so when we were doing the pendulum problem, we made use of this small angle approximation. And so let's take advantage of the fact that we now know that bit of information and let's make some use of it. So what we're essentially saying is, maybe we're going to make the value of Q small so that there is a repulsive force between these masses, but that force is not so strong. And so they repel just a little bit and we have a small angle between the vertical and these strings. So we know that for small theta, we can approximate sine theta is approximately equal to theta. That's what we used for the pendulum problem, and so we're going to use it again. Okay. Now we're going to want to do something similar for cosine theta, but before we do that, let's just plot sine theta and see if we can understand in this picture why this approximation works well. So we're going to plot sine theta as a function of theta. Okay, so we know that when theta equals 0, sine theta equals 0, and so it's going to sit here, and then it's going to go through some peak. That peak is at pi over 2, then it'll oscillate sinusoidally like so, and it'll go backwards as well. So that's not a perfect sine function, but you get the picture. So if we're restricting ourselves to small values of theta, then we're kind of limiting ourselves to values that are very close to that vertical axis. And what we can notice is that close to theta equals 0, the intersection of our coordinate system, that red line looks almost just like a linear function. So it's like theta is just increasing linearly. And so that's exactly this approximation. Sine theta is approximately theta. So we approximate this curved oscillating function as the straight line, as long as we stay close to the origin of our coordinate system. So that's really what we're doing, is we're approximating sine theta as a straight line near the origin. Okay, so that's an interpretation of our small angle approximation for sine theta. So let's see if we can do something like that for cosine theta. So here we'll plot cos theta, and this will be theta. Okay, so what do we know about cosine theta? When theta equals 0, cos of theta is 1. And so 1 is over here somewhere. Okay, and then, it oscillates, it looks just like the sine function, it's just shifted a little bit over. And so it will go to 0 at pi over 2, it'll go to -1 at pi, and then it'll just have this periodic oscillation. Okay. So if you look at that picture of cosine theta, what would you approximate cos theta as if you were going to if you're going to restrict yourselves to only very small values of theta? So 1, right? That's exactly right. In fact, what we can do is we can draw a tangent line to the cosine function when theta equals 0. And so right at theta equals 0, of course, the cosine is 0. But if we move a little bit away from theta equals 0, the function drops a little bit, but only a little bit. And so as long as we don't move too far away from small values of theta, cos theta is approximately 1 is a good approximation. So for theta very small, we can approximate cos theta is approximately equal to 1. Okay, and so what we're going to do is we're going to use these two approximations in the problem we were working on over here. And so we have cos theta divided by sine theta cubed. And so what we're going to do is for small angles, we can approximate. So it was cos theta divided by sine cubed theta as 1 divided by theta. And then we have to have 3 factors of theta because we have a cube of sine theta. Okay, so then if we go back to star, so let's see, let's call this equation star 4mg L squared over kq squared. So then star becomes, well, 1 over theta cubed is approximately, what was it, 4mg L squared divided by Coulomb's constant q squared. Is that what we had? 4mg L squared, yeah. Okay, and now we can solve for theta, so such that theta is approximately, so we're gonna have to just invert everything. Coulomb's constant q squared divided by 4mg L squared, and then we take the cube root or raise everything to the 1/3 power, and this is now a solution for the angle theta in radians. Okay, and what you can do is you can kind of check. It's a good idea to see if this makes some physical sense to you, some intuitive sense. Our results suggest that if we make the charge bigger, then the angle theta will get bigger. And of course that makes sense. If I make my charges bigger, they repel one another more strongly and theta increases. If I make m larger, then the gravitational force is stronger and that angle gets smaller. And so you can make those kind of simple checks to see if this result makes intuitive sense. Yeah.
Will this work for degrees too?
No, it won't work for degrees. And the reason it won't work for degrees is because these approximations, sine theta is approximately theta and cos theta is approximately 1, only works if you have theta in radians. Yeah.
What's the accuracy for that cosine theta?
Well, you could just, it's probably similar to the sine one, like around 15 degrees. There's no hard rule for that. It's how precise do you require your calculation to be, right? So it might be different in different scenarios. Okay, good. So what I want to do next is to revisit this Coulomb's law, but I want to see if we can include more information. Coulomb's law is an expression for force, and force is a vector. So it has a strength, a magnitude, and also a direction. What we wrote down at the beginning of class was just an expression for only the magnitude or the strength of the force. How do we go about including the direction? So vector form of Coulomb's law. All right. So the goal is to include direction information. So goal include information about the direction of the force in Coulomb's law. All right, so I'm going to draw a picture similar to what we had before. So we'll say we have some charge Q1 over here, and then some distance away, we have a second charge Q2. And if I draw some perpendiculars, what we can say is that the distance between these charges is R. Okay, So what we can do is we can write down the magnitude of this force. It would just be Q1, Q2 divided by R squared times Coulomb's constant. Okay. But what we're going to do is we're going to define a unit vector. And so I'm going to call this unit vector R hat sub 1, 2. Now, I assume that you've used unit vectors in physics 111. So for example, you may have used like I hat or X hat as the unit vector along the X axis, J hat or Y hat along the Y axis. And maybe if you did anything with the Z axis, you could use K hat or Z hat as a unit vector along the Z axis. So a unit vector has only two properties. One is that its length is always 1. So no matter what, if you call something a unit vector, unit means 1, and so it has a length or a magnitude equal to 1. And its other property is just a direction. And we get to choose how we specify that direction. Could be along the x-axis, y-axis, z-axis. In this case, what we're going to do is we're going to define the direction of this unit vector to be along the line that connects the two charges. And specifically, it's going to point from Q1 towards Q2. So this is going to be a vector of length 1. And so what that means is if I was to evaluate the length or magnitude of this unit vector, we'd always get 1. Okay, and then we're going to say that this unit vector points from Q1 to Q2. And so what we'll do is we'll draw it on our picture here. So this is, let's say this is our length of 1, and it's going to point from Q1 to Q2. So now let's just think about this for a second. If these two charges, Q1 and Q2, were the same sign, both positive or both negative, there would be a repulsive force. So if I was to ask then, what is the force on Q2 due to Q1? We would say it's repulsive. It's along the line that connects the two charges. And in fact, it's going to be exactly parallel to this unit vector that we just drew. And then we say, okay, well, what if Q1 times Q2, like what if they were opposite signs so that their product is negative? One's positive, one's negative, then it's going to be an attractive force, and that force on Q2 will be towards Q1, or it'll be anti-parallel to this unit vector that we just defined. So if we say the product of the charges is positive, it's a repulsive force, and it's in the direction of R hat 1, 2. If the charges are opposite, it's an attractive force, it's in the direction anti-parallel to R hat 1, 2. Okay, so let's summarize those observations. So we're going to consider the vector equation. So we'll write this as F1, 2. This is going to represent the force on Q2 due to Q1. And so we're going to write it as Coulomb's constant, the product of charges divided by the distance squared. That's the magnitude part. That's what we had last class. And now the thing that we're going to add is just the unit vector. Multiplying by the unit vector doesn't change the strength of the force at all, because the unit vector has a length of 1. All it does is it specifies the direction. And so now we consider the two possible cases. So these would be like charges. For like charges, Q1, Q2, if we take their product, it's positive. And it doesn't matter if they're both positive or both negative. They're in both cases, they're like charges and the product will be positive. Okay, so this could be 2 positive or 2 negative charges. Okay, so in this case, the force on 2 due to 1 is parallel to r hat 1, 2, or it's in the same direction as r hat 1, 2. And our vector equation handles this perfectly because as long as that product of charges is positive, this force will be in the same direction as that unit vector. All right, and then you can probably see what we're going to do is we're going to say, okay, if we have opposite charges, 1 positive and 1 negative, 1 positive and 1 negative, then this product Q1 times Q2 will be negative. And then when we plug that into our vector equation for this force, we're going to have some negative quantity times this unit vector. And that negative sign just means that the direction of the force is anti-parallel to this r hat 1, 2. So in this case, F is anti-parallel to r hat 1, 2, or it's in the opposite direction of this unit vector. All right. And so this works. This is the vector equation for the force on Q2 due to Q1. And it has all of the same magnitude information plus now the direction. Okay, and so we'll have some, we'll make use of this, in fact, very shortly. All right, so we're now in the situation where if we have 2 charges, it kind of nearby one another, we can talk about how they interact, how they exert forces on one another. What we're going to do is we're going to try to abstract, we're going to try to make some abstractions that will hopefully be useful. So, you know, these forces, this electric force is a little bit odd, right? Because there's no physical contact between these charges, and yet they still exert forces on one another. Gravity is another one that does that, but all these other forces like friction and tension and I don't know, what are some of the other common ones that we use, normal force, they all require some direct contact between the 2 bodies that are interacting with one another. But here we have a gravitational force and an electric force where they don't have to touch one another. And what we're going to do is we're going to introduce the concept of a field. And the idea is that if I take some charge Q and I place it in space, it creates an electric field that permeates all of the surrounding space around it. And then if I take a second charge and put it nearby, the electric field that the first charge created exerts a force on the second charge. And we could do the other, you could do it the other way. We could say, okay, when I put in the second charge, it makes its own electric field, and that is going to exert a force on the original charge that was in place. So what we could have is when we have charges in our space, there's electric fields around, and we know that if we have other charges around, that they'll interact with that electric field. Okay, so let's see how this is going to work. So this is section 5.4 in OpenStax University Physics, Volume 2. And so we're going to start talking about the electric field. Okay, so we will use the symbol capital E for electric field. I've drawn it with a vector symbol, so it's going to have a magnitude and a direction. In fact, you could have guessed that it would have to, because we've already said it's going to be used to help us calculate forces on charges. So if forces have magnitudes and directions, then our electric field will as well. All right, so the idea is that a charged object generates an electric field that exerts forces on other charges. And so it's useful to keep in mind that this idea of the electric field is very analogous to the idea of a magnetic field. So just like, you know, the Earth is exerting a force on the moon. So the picture that we have is that the Earth creates a gravitational field that surrounds, that permeates all space. The moon is some massive object in that gravitational field, and that field exerts a force on the moon. The moon also creates its own gravitational field that exerts forces on the Earth and other nearby objects with mass. Okay, so the idea is maybe we have some distribution of charge. We can call it capital Q, so we'll draw a bunch of positive charges here. And so what we could do is we could go to some point in space, and so we could say this is some point P1, and at P1, this is the electric field E1 due to this charge distribution Q. So this is the electric field at P1 due to Q. And then we could go to some other point in space. Maybe we'll go to a point over here, and maybe we could try to measure the electric field at this point. Maybe this is point P2, and this is the electric field E2, and so this is the electric field at P2 due to Q. And so we'll see in a second how we're going to determine the strength and the direction of this electric field. But I've kind of drawn in here some things that might make intuitive sense, even though we haven't said much about this electric field yet. First of all, point P1 is farther away from the charge distribution than point P2. So I drew the electric field at 1 as being shorter in length than the electric field at 2. And so we're going to have this idea that, of course, when charges get closer together, their repulsive or attractive forces grow stronger. And so if the electric field is going to be exerting these forces, they must get stronger as you get closer to the source of charge. Okay, and the position of P2 is in a different orientation than P1, and so I've drawn this electric field as having different directions at these 2 points. All right, so the idea that we're going to follow in order to make this a more quantitative discussion is to determine, let's say, to determine the electric field at a point due to Q. What we're going to do is we're going to place a small test charge. So we'll call it test charge Q0, and we're going to measure the force on it. Okay, so let's imagine we have some large distribution of charge, and then we take some small charge. The reason we say small is because I don't want this little charge to cause a rearrangement of the distribution of the original charge. And so the big chunk of charge does not change much due to the presence of the small test charge. And then we're going to place it at different positions, and in every position, we'll measure the direction and the strength of the force, and we're going to use that to calculate the electric field that it's experiencing due to capital Q. Okay, so that's the plan. And so by definition, the force on our test charge Q0 due to this big distribution of charge Q is given by, okay, so the force on Q0 is going to be equal to Q0 times the electric field. So let's just be clear, this is the force on Q0 due to Q, and this is the electric field due to capital Q. All right, so what this means is that if I know Q0, if I choose its value, and if I make a measurement of the force, I can just take that force divided by Q0, that tells me what the electric field is. Okay, so as a picture, what we would have is Q, our big distribution of charge, and then over here, we have at some point, we place our test charge Q0, and let's imagine, just for the sake of this drawing, that it's a positive test charge. Then we're going to have a repulsive interaction between these two, like the like positive charges are going to repel one another. And so this would be F0 would be the force. And if I divide by Q0, so we would know that E would be F0 divided by Q0. The electric field is going to have the exact same direction as this force if Q0 is positive. So the electric field at this point will be parallel to F0. We're just going to scale its size by dividing by Q0. And if Q0 is a small charge, then maybe we're dividing by a small number. And so we get this electric field of something like this. And then we can just go and take this little test charge and move it at a bunch of different points around this Q0, and we would find what the electric field looks like at all points in space. Okay, let's check the units of this electric field. The units of the electric field. Oh, shoot, sorry. So the units of the electric field are equal to the units of force divided by the units of charge. And so our force is going to be measured in newtons, and our charge is measured in coulombs. And so our electric field is in units of newtons per coulomb. Okay, so the next thing we're going to do is we're going to try to figure out what the electric field due to point charges is. And we're going to make use of what we know about the electric field, that the force is Q times E. That's by definition. And we're going to make use of what we know about the interaction between 2 point charges, Coulomb's law. We'll combine those two things and see what happens. Okay. So what we're interested in now is the electric field between, let's say, due to a point charge. Okay, so we'll have our point charge, capital Q, and some distance r away, we'll place our test charge Q0. All right, and so this distance is going to be r. And well, so the force on Q0 due to Q is, well, one way to write it is F0 is equal to Q0 times the electric field, whatever the electric field due to capital Q is. And the second way is to use Coulomb's law, which says that the force on Q0 is going to be Coulomb's constant times Q0 times capital Q, the product of the charges, divided by the square of the distance between them. And then we have to give a direction, and I'm going to call this unit vector r hat. I'm not going to put the 1, 2 subscripts, but let's say r hat is a unit vector that points from capital Q to Q0. Then Coulomb's law tells us that the force is given by that second expression. So we have Coulomb's law. Okay. Well, these two forces, they're two expressions for the exact same force, and so they must be equal to one another. And so it must be the case that Q0e is equal to Coulomb's constant Q0 capital Q divided by r squared times r hat. Both these expressions have Q0, and so we can do that cancellation. And so finally then, the electric field due to capital Q is given by E is Coulomb's, Coulomb's constant times capital Q divided by r squared times r hat. So the electric field of a point charge capital Q. Okay. And so that's what the electric field is always going to look like for a point charge. One thing we could notice is that if capital Q is positive, this electric field will be in the direction of r hat, and r hat was pointing away from the point charge. If capital Q is negative, then we'll get some negative number times r hat, which means that the electric field will point in the opposite direction. So the direction of the field is determined by the sign of the charge. So let's try to map out the electric field of a positive point charge. Okay, so let's put our positive point charge over here. This is going to be Q, it's greater than 0. And all we're going to do is we're going to go to different points, and we're going to think about what this expression kq over r squared times r hat is going to look like. So we first go to a point over here, let's say. And what did r hat do? R hat pointed in the direction of that point starting at Q. So if we were to draw our unit vector, it looked like this. And so that means the electric field at this point for positive Q will be parallel to this r hat unit vector. Okay, and so the electric field over here would look something like this. all right? And then what we do is say, okay, let's go to some new point. I'm gonna go to a point over here. And what we say is, all right, the unit vector that I would have would be pointing from Q towards that point. So in fact, it's the same unit vector in this case for these 2 points because they follow on the same line. But now the distance between Q and this second red point is smaller. So we're dividing by r squared, and if we make r smaller, we're dividing by a smaller number. So the electric field is stronger. So I'm going to draw it as being a longer vector. Okay, and then we just keep going, and we say, all right, let's pick some new point over here. Now my r hat points from Q to the point. This one's pretty far away from Q, so we get a small electric field. And then we just keep going, and we do this over and over and over again for a whole bunch of different points. And what we're going to find is that the electric field, of course, is going to be strong when we're close to the charge, and it's going to be weaker when we're farther away from the charge. And it's always going to be pointing radially away from this charge. And so this is now the electric field due to this positive point charge Q. And, you know, I can't draw vectors at every single point in space, but in principle, you could put your point anywhere you want, and you would always be able to map out the electric field in this way. I can do that one a bit better, I think. Okay, and so the electric field looks something like this for a positive point charge. Now, it's a little inconvenient to have to draw a whole bunch of discrete vectors to represent this field because, like I was saying, there's an electric field at every single point, and I can't draw it at every single point. So what people usually do is they draw continuous lines to represent the electric field. So usually draw the electric field lines. Oops. As continuous lines. So let me show you what it looks like, and then we'll figure out how to interpret this picture. So I'll draw the same point charge, capital Q, and I'll make it positive. So usually what the electric field would be drawn like would be the following. They don't draw these short little vectors with tails at every point in space. They draw continuous lines coming from the point charge itself. And so it would look something like this for a positive point charge. So that raises a question. It's still pretty clear what the direction of the electric field would be at all points. Wherever you're sitting in this space, if you draw a line that's radially pointing away from that charge, that's the direction. But how do we, like in our previous picture, I had short vectors for weak electric fields, and I had long vectors for strong electric fields. How am I going to interpret the strength of the electric field from a picture like this? Does anyone have any ideas? Yeah.
You just know that as you get farther away, it's because we perfect on things.
Yeah, I mean, that's true, but I mean, maybe I could have some complicated picture where I have a complicated arrangement of charges, and I don't really know actually if I'm getting closer or farther away. So what would I do in that case? Yeah. Pardon me? Yeah, we could draw arrowheads, but if I didn't want to change this picture, like, what could you tell me about the electric field lines when I'm close to Q? Yeah. Yeah, But how could I get that information from the picture? Yeah. Yeah, it's the density. It's how closely spaced the lines are. When the lines are closely spaced, the electric field is strong. When the density is low, when there's lots of space between one line and its next neighbor, that means the electric field is weak. So in this picture, the density or the spacing of the electric field lines tells us the strength of the electric field. Where lines are closely spaced, E is strong, E is weak, where the lines are, I don't know, spaced further apart. Or where there's a low density of those lines. Okay, good. So I've got a couple minutes. What we're going to do is, let me just draw the picture for the electric field due to a negative point charge. And we could do it in a similar kind of way. So here, I'll leave this up in case you're still writing. Let's draw over here, Q is less than 0. And so this will be a negative point charge. Okay, and so for a point charge, E is Coulomb's constant, Q divided by R squared, R hat. All right, so we'll do it first in this method where we kind of draw different points. And so I could take a point over here and I could say, all right, R hat is always going to be from Q to whatever our point of interest is. And so there's our R hat. Now, if Q is negative, KEQ divided by R squared is some negative number. So it's a number with a minus sign times R hat. So we have minus R hat is our direction. And so we are anti-parallel to this R hat. And so the electric field at this point is something like that. Okay. And then if I take a point over here, I would have exactly the same argument for the direction, but the magnitude would be stronger because now R, the distance between my point and Q, is smaller. So I divide by a smaller number, and I therefore get a stronger electric field. Okay, and so we would get an electric field that would look something like this for our negative point charge. And so I'll draw just some of these. I won't draw a million of them. Okay, and so for our negative point charge, the electric field is still radial, but it's radially inwards towards the point charge. And just like we did for the positive charge, we would typically draw these as continuous lines. So you would usually see this drawn in the following way. So here's going to be Q is negative, and the electric field is going to be radial, but it'll be radially inward. And so this is the electric field due to our negative point charge. Okay, good. So I think that's probably where I'll stop. What we'll start with next time is superposition principle. And so the idea is, if I have a bunch of point charges throughout space, and then I place a test charge at some arbitrary position, how do I figure out the net force on that test charge? And if that test charge is not there, how do I still figure out what the net electric field due to all the other charges is? All right, thanks very much.